In this video, we're going to start looking at partial derivatives. Okay, so this kind of opening slide here about finding the derivative if a is a constant. You'll see why I'm doing this in just a minute. So f prime, of course, treating a as a constant, then we would have 18a x squared, just like that. This one, f prime, well, the derivative of the outside is cosine, and we would leave the inside alone, so ax plus x squared, and then we'd multiply by the derivative of the inside, which would be a plus 2x. And finally, this last one, we're going to need a little quotient rule. So f prime of x, low, d high, minus high, d low, cross the line, square the low. And just in the interest of time, I'm going to stop, even though, of course, you could probably do some simplifying here. But I'm just going to stop there. Okay? Let's start talking partial derivatives. A partial derivative is used to analyze how a function is moving in three-dimensional space. So, oddly enough, it feels like it should be a lot more work. We actually begin kind of looking at each variable separately. So how we denote this is with kind of a script D, so delta f respect to x. And what this does is we're going to find the derivative with respect to x and treat y as a constant. So a lot of times you'll just see people write the y squared out front, and they say that's just a constant, and then the derivative of 7x cubed, I guess, would be 21x squared. And you probably want to write it back like this. But that's it. That's the partial derivative of f with respect to x. So the partial derivative of f with respect to y, again, you kind of just see these constants left out front. The derivative of y squared is 2y. So the answer would just be 14x cubed y. Now, the next one, f of xy equals y squared over 1 minus x squared. Well, the partial derivative with respect to x, you could certainly do this still with quotient rule. Just remember that y would be treated as a constant. So we'd have low, d high, and the derivative at the top would be 0. Because remember, we're treating y as a constant. Minus high, d low. Cross the line and square that low. So this, of course, this first part would multiply out to be 0. We'd have positive 2xy squared over 1 minus x squared squared. And that's your partial derivative with respect to x. So your partial derivative with respect to y, we'd have low d high minus high d low, and the derivative of the low, since it's all a constant, the derivative of the low is 0. Cross the line and square the low. Okay, so here, this would multiply to be 0, so we'd have something like 2y minus 2yx squared over 1 minus x squared squared. So again, partial derivative with respect to x means treat y as though it were a constant. A partial derivative with respect to y means treat x as though it were a constant. Let's do a couple more. This is another way of writing a partial derivative, and this notation here with the sub x like that, this means partial derivative with respect to x. So let's do that. So we're treating y as just a constant, so the derivative of x cubed is 3x squared. So it's 3x squared y. And we said to evaluate this at x equals 1 and y equals 2. So 3 times 1 squared times 2, it is 6. So that's the value of the derivative. Now how that helps us, that describes the slope in simply the x direction. Okay, so simply in x, this is how the function is moving. And again, that's going to be useful for us as we begin to work with tangent planes. But for now, we're just calculating the derivative. So this would be the partial derivative with respect to y. So now we're treating x as a constant, so it'd just be x cubed times 1. Evaluate at 1, 2. So 1 cubed times 1, this is just 1. Okay, that's it. So partial derivative with respect to x, treat y as a constant. Partial derivative with respect to y, treat x as a constant.